Welcome to Mitten Made Infrastructure's Shaw Lane Power Plant Renovation presentation. Before talking about the project, we will be going over quick introductions of everyone on our team. My name is Lauren Foytek and I'm the project manager for Mitten Made Infrastructure. I'm an environmental engineering major at Michigan State University and I will be graduating this semester. I have had 5 different engineering internships at Consumers Energy throughout my college career, including working under project managers for a multi-million-dollar pipeline project.
Hi, my name is Emma Davis, and I am one of the environmental engineers for the Mitten Made Infrastructure team for CE 495. I am a current environmental engineering student at Michigan State University, and I have a double minor in energy and environmental and sustainability studies. My expertise and past work experiences include PFAS remediation, water treatment, and NEPA construction compliance.
Hi, my name is Marta Gappy, and I worked on the environmental team for this project. I am an environmental engineering major at Michigan State University. I have had experience working for multiple general contracting firms, and I will be working for an engineering consulting firm doing development services after graduation.
Hi, my name is Anna Keller. I'm a senior environmental engineering student working as the hydrology engineer on this project. I'm experienced in using AutoCAD to translate data and create maps and construction designs, and I've assisted with the drafting of environmental documents and reports for MDNR, EPA, and EGLE.
Hey guys, my name is Liam Armstrong, and I've been Mitten Made Infrastructure's structural engineer for CE 495. Throughout my time at MSU, I've held 3 internships, including my current position as a geotechnical engineer intern at FK Engineering over in Madison Heights, Michigan. I'll be graduating in a couple of weeks as a Spartan civil engineer. Go Green.
Hello, I'm Dobie Bonev. I'm the pavement engineer for our group. I'm a civil engineering major. I have interned 1 summer at Wayne County Field Services and 2 summers at the Road Commission for Oakland County. So overall, I have 3 years of inspection experience across Michigan roads.
Hi, this is Zhu Dongniu. I'm a civil engineering major and I'm the transportation engineering in this project. I got an internship in China in 2019, which associates with the General Transportation Plan for new buildings.
First, we will discuss the project scope and setting. The location of this project is at Michigan State University. Located in East Lansing, Michigan, MSU is a public university with almost 50,000 students and over 400 academic programs. Michigan State University's 2020 Vision Campus Master Plan detailed plans for community growth and new infrastructure. An existing piece of infrastructure that is a landmark on MSU's campus is the Shaw Lane Power Plant. This coal plant has not been used for decades and will be renovated with an additional building added onto it. The building will be the STEM teaching and learning facility geared towards STEM-related learning for students on MSU's campus. Also, the segment of Shaw Lane between Chestnut Road and Red Cedar Road will be restored. Mitten Made Infrastructure's goals for this project include renovating Shaw Lane Power Plant and adding additional space while keeping the best features of the surrounding buildings. We will design and repair roadways and walkways in order for those on campus to travel safely and in a timely manner. Lastly, we will focus on providing an energy-efficient building and to not only protect but create new green space in the areas surrounding the building. While this project focuses on the renovation of Shaw Lane Power Plant and nearby roadways, we would like to briefly highlight research our environmental engineers did these last few months on COVID-19. Understanding this virus is important because of the effect it has had on our daily lives and possibly how we will operate in the future.
Before we get into our project scope, environmental engineers on this team and within the CE 495 class were tasked with a separate project which included decay modeling of SARS-CoV-2 and wastewaters. So essentially a background on this specific report that we had to do was essentially writing a literature review on specific decay modeling that is currently in the works within literature, as well as doing our own modeling within Sumo software and publishing our results within a technical report. Within background of SARS, full name for SARS-CoV-2 is Severe Acute Respiratory Syndrome Coronavirus 2. Its origins come from China within late 2019, and it spread into the globe around February and March of 2020. This is a positive sense RNA, which means that it mainly attacks the human respiratory system, although there are also other parts of the human body that it can attack as well, such as the digestive system and other, etc. There are multiple pathways for transmission. There is known person-to-person contact of SARS-CoV-2. There is also known transmission through aerosols and through inhalation of aerosols. And in the United States, there is 1.12 million cases total and 220,000 deaths as of October 20th. Within the water treatment realm, there are calls to preventive measures. An important facet of the wastewater treatment process is detecting viruses and epidemics that could occur within the wastewater treatment system. Since SARS viruses can be shed through human fecal matter, this can be used for our benefit to detect how much of an issue a local community could have when it comes to SARS-CoV-2. So many communities are looking to create preventative measures in order to deter the severe impact that this virus has the potential to formulate. As stated in our project prompt for the specific type of work that we were doing, wastewater-based monitoring of this virus can greatly serve as an early warning system for potential outbreaks within a community. So we did a literature review to analyze and serve as guidance for determining certain design aspects within the wastewater treatment process, such as pH, temperature, and flow rate, that could be relevant in determining decay of SARS-CoV-2. Within a specific literature, Ahmed et al., there was an attempt to provide further research in terms of SARS-CoV-2 decay characteristics. They utilized real wastewater samples from a local wastewater treatment plant in Australia, and the goal of this study was to compare the decay characteristics of SARS-CoV-2 in various media by measuring through RT-qPCR. Untreated wastewater, autoclaved wastewater, and dechlorinated tap water were stored at 4 degrees, 15 degrees, 25 degrees, and 37 degrees Celsius, and they were subject to SARS-CoV-2 RNA to assess the effect of the water matrix type and temperatures commonly relevant within the environment. To combine both of those 3 solutions and 4 different temperatures, 12 microcosm samples were created and tested, as shown in the images on the right of your slide. The solutions were seeded with the viruses and incubated and sampled over the course of 33 days, and the temperature was the parameter that had the most effect on first-order decay, with significant changes in decay rates. As seen in the table to the left, there were specific virus parameters that we used for our software design. These were found in our untreated wastewater samples at temperatures of 4 degrees and 25 degrees. We used these decay rates that were found within Ahmed et al. For our Sumo design software. Those can be found highlighted in the slide. For design purposes, our team focused on 2 different wastewater treatment steps: integrated fixed film activated sludge and moving bed biofilm reactors, which can be shown on the top left and top right images within this chart. For design purposes, Sumo 19 software was used for both of these processes, with the addition of a digester as seen in the bottom left and the bottom right. We assessed papers, and those were used to benefit our understanding of how each of these wastewater treatment steps worked in aiding the decay of SARS-CoV-2 in simulated wastewater. SUMO is a wastewater process simulation software used by many environmental engineers around the world, and one of its many advantages is that it can run a simulation for virtually any wastewater treatment plant, new or old. It can maneuver even the most complex plants, digestion, nitrogen, and phosphorus removal, membrane bioreactors, primary and final settling, and many others. With this in mind, SARS-CoV-2 was used as a contaminant in the wastewater to investigate the effluent concentration of viral RNA. We inputted plant designs which included daily flow rates along with decay rates from Ahmed et al., and these were modeled with the influences of measurements. We decided to create a macro Excel spreadsheet from a SUMO design spreadsheet that was already used to assess our SARS virus count over time within a period of 100 days. SARS decay within IFAS and MBBR was designed using the SUMO software, and parameters were defined within SUMO to imitate the Colorado plant that was within our study of focus at both high and low temperatures. Within the low temperatures, parameters used was temperature of 4 degrees Celsius, a flow rate of 6.7 million gallons per day, and a decay rate of 0.084 days to the -1. As seen in the chart that you are currently looking at, these are our results for our summer model, which contained a temperature of 25 degrees C, flow rate influent designed at 8.0 million gallons per day, and the virus decay at 0.183 days to the -1. For low temperature virus decay, the effluent showed a gradual decay of the virus for 100 days. As you can see, we started each model at a virus count of 100 viruses. Obviously, our design was on a much smaller scale, but this gives great promise for future recommendations. Within the IFAS, the MBBR step showed an increase in a logarithmic increase over the 100-day period, which is expected based on the nature of MBBR and the buildup of biomass. But high temperature decay showed a lower virus count overall in both specific wastewater treatment steps. The virus count in the effluent started gradually stabilizing from day 1 to 100, and lower counts were expected because at higher temperatures, the virus decay rate increases due to the inactivation of the virus at higher temperatures as well as the higher decay rate. Throughout both results, but more specifically, there was a short increase in MBBR, a logarithmic increase within the first few days, but IFAS continuously logarithmically increased, showing that MBBR was potentially a more effective tool in activating SARS within a wastewater treatment system.
Thank you, Marta and Emma. Next, we will be moving into the engineering designs for the Shaw Lane power plant renovation.
The structural engineering portion was divided into 3 reports. The first report established the structural and architectural layout of the 2 steel frame buildings. The second report utilized the SAP 2000 program to calculate the design loads on the structures. In the third report, I used those loads to design the steel members used throughout the building. And finally, I developed the cost analysis for the structural portion of this project. I'll explain these steps in more detail in the coming slides. The first step in Report 1 was to decide on the location and orientation of the 2 steel frame buildings. I decided to have the 2 buildings situated in an L-shaped pattern. For simplicity purposes, I've named the building that is further north the north building, and yeah, you guessed it, the building that is further south is the south building. As you can see in the figure, the eastern side of the north building is butted up against the pre-existing Shaw Lane power plant. This orientation was chosen to avoid the existing subsurface utilities like water and gas lines. It also allows pedestrian traffic from Red Cedar Road and the Spartan Stadium parking lot. After the location of the buildings was determined, I moved on to the structural design. The north building was designed to have a footprint of 160 feet by 80 feet. The south building is nearly identical except for an additional 32-foot set of columns, making the footprint 192 feet by 80 feet. I chose to space the columns on the long side of the buildings 32 feet apart, as seen in the two figures in the top of the slide. Having all of the columns spaced 32 feet apart makes the building symmetrical, which leads to a more stable structure. It was suggested to use smaller offsets like 20 feet apart, but I decided to use 32 to cut down on the amount of steel, thus cutting down on the cost. The short side of the buildings are identical, with 30-foot spacings on the outside and a 20-foot space in between. This allows for large classroom sizes on the exterior of the building and a wide main corridor through the middle. One of the design requirements was that both buildings had a basement plus 4 stories, but the buildings could not be more than 65 feet above ground surface. In my design, the basement level is 14 feet tall to allow for large machinery and utility equipment. The first floor was designed to have tall 15-foot ceilings for aesthetic purposes. The second floor is 14 feet tall to allow for lab equipment, and then the third and fourth floors are both 12 feet tall, as they are primarily used for smaller classrooms and offices. Including the trusses, the buildings are both 63 feet above ground surface. Another important detail is the added bracing members on all 4 sides of the exterior of the buildings. Brace frame buildings are approximately 40% cheaper to build than moment frame buildings, so it really helps to cut down on the costs. For the architectural layout, there were requirements for the size and number of offices, classrooms, labs, and other rooms. These requirements are shown in the chart on the left. The chart on the right shows the size and number of each of the room types that I designed for. The next 3 slides show the floor plans for each of the floors on the building. The basement level has 4 large labs, 2 in each building. You can also see that there are 3 staircases in the north building and 2 in the south building. Along with the staircases, there are 2 elevator shafts in each building. All of the elevator shafts contain 2 elevators. The locations of the stairs and elevators are consistent through each floor. Also in the basement of both buildings are room for storage, mechanical services, and electrical services. The first floor, seen on the left side of this slide, contains all of the computer labs and both of the dean's offices. There are also 3 large classrooms and 1 medium-sized classroom on the first floor. The large 1,480 square foot classroom in the southwest corner of the south building would be ideal for larger lectures. As for the second floor, seen on the right side of the screen, there are 9 medium-sized classrooms, 1 large classroom, and 5 labs. One of the labs is over 1,600 square feet and would be ideal for large lab equipment. I made sure that every level of both buildings had plenty of restrooms. Also, most of the floors have closet space for janitorial storage. The third floor is pretty similar to the second. It has 12 medium-sized classrooms, 1 large classroom, and also has that big 1,600 square foot lab. The fourth floor is designated for all the department and faculty offices. The north building has a department office, 13 faculty offices that are 320 square feet, and then 7 smaller faculty offices. South building also has a department office, plus 17 faculty offices that are 320 square feet, and then 10 smaller offices. After Report 1 was accepted, I moved on to Report 2, Design Loads. Since the north and south buildings are nearly identical, they would experience similar loads. The south building, being the larger of the two, was used for the loading calculations. Dead loads, live loads, roof, wind, and snow loads were all calculated and then input into the SAP 2000 software. Once all the loading types were applied to the structure in SAP, the load combinations had to be established. The combinations shown on this screen are standards set by the ASCE 7-16 manual. Every beam, column, truss, and bracing member was evaluated to experience all 6 of these load combinations. From there, SAP displayed the load combination that caused the largest amount of stress on each individual member. That being said, when I would move on to the designing of the members, I designed each member for the maximum loading that it could experience, rather than designing the entire structure based off of one of these load combinations. So now that the design loads have been calculated, I moved on to designing the members to withstand these loads. I used the maximum loading that was given from the SAP 2000 file to design each member, but for visual purposes, I've included the tributary areas that correlate to each member on this slide. In general, the larger the tributary area, the larger the force applied to that beam or column. So, for example, in the figure for the beam tributary areas, the 475 square foot section area will generate a larger force than the 255 square foot area. I'm not saying that each 475 square foot section will experience the exact same force, but it is within a range of 3%. With this generalization, I was able to design 2 W-shaped beam sections to be used throughout the entire structure. The W12 by 58 beam would support all of the tributary areas that were 255 square feet or smaller, and the W14 by 82 beam would support all of the tributary areas 475 square feet or smaller. Although I could have designed every beam in the structure for the exact loading that it experienced, that would just be impractical. Instead, I generalized each beam with a sufficient degree of safety. By only using 2 W-shaped members for all 332 beams in the building, we would be able to buy these sections in bulk and save money. The AISC manual for W-shaped structural steel was utilized to design these members, and a similar process was used for the columns, trusses, and bracing members, all of which were designed with a proper degree of safety. Once I designed all the members to properly carry the maximum loads, I could move on to the cost analysis. For steel, I used the approximate unit price of $4 per pound for structural steel. I compiled the weight of all the beams, columns, truss members, and bracing members for both buildings, then multiplied that weight by $4 per pound. Before doing this, I made sure to include 20% of the total weight for bolts and welded connections, and 20% of the cost for construction and fabrication. For concrete, I used a unit price of $145 per cubic yard to multiply by the total volume of concrete between both buildings. I added 20% volume for material loss and 25% of the cost of construction. Cost analysis was also made for rebar and the cost of design. Combined all together, the preliminary cost for the structural portion of this project is about $6.2 million.
The responsibilities of the hydrology engineer were broken up into 3 reports. Part 1 of the hydrology design was incorporated in the first report. The objectives of the first report included reviewing the Ingham County Drain Commissioner's rules and regulations for stormwater management and making sure, as the hydrology engineer, that I was familiar with all of the regulations my stormwater design needed to meet. Preliminary research also involved in the first report included reviewing the existing storm drain network on the project site and identifying inadequacies in the system. After identifying the present inadequacies, design solutions were proposed. The first design solution was to redivide the project area into subcatchments. These subcatchments will more efficiently follow the natural topography of the project site, so it will direct runoff into the stormwater system with ease, which eliminates the need for serious grading of the site or pumping of water. Once these catchment areas were outlined, a conceptual engineering design of the drainage system was drafted. Part 2 and Report 2 of the design included further development of the engineering design for the stormwater system. This included placing manholes, inlets, and pipe network into the project area, and performing a hydrological analysis of the pipe network, which included surface runoff volumes, pipe flow and sizing, and storm drain sizing. In the final leg of the design, or Part 3, a stormwater retention or detention basin was designed and sized for the network, as well as an outlet system for the stored runoff. Hydrological analysis was also performed for the retention and detention basins and outlet systems, and these analyses included surface runoff, storage routing, flow through the detention basin, sizing of the outlet pipes, and quantifying the impacts of the storm water detention basin on peak flows. To begin the design, the first step in the process was to review the new rules and regulations from the Ingham County Drain Commissioner rules that would influence the stormwater network design. After reviewing these rules, the key objective was that the new system design needs to ensure that the volume, rate, timing, and pollutant load of runoff over the project area remains the same or less than what occurred under natural conditions, and this is referring to the pre-development runoff rates. The rules also outline design criteria for detention and retention basins. For the detention basin, a 100-year storm event must be managed. The detention basin also needs to be able to store and treat the first half inch of runoff over the entire project area. And the detention basin also needs an outlet system that will, again, not exceed the pre-development runoff. And then for a retention basin, the basin must be able to manage 2 100-year storm events, and in contrast does not need an outlet. So I decided that the implementation of retention basins over detention basins would be the most effective method to keep the post-development runoff less than or equal to the pre-development runoff, because there does not need to be an outlet system for the retention basins like there would need to be for the detention basin, and also the retention basin does not need to be able to store that first half inch of runoff. As discussed in Part 1 of the responsibilities of the hydrology engineer, the first step in the conceptual design process for the stormwater sewer system was to redefine the catchment areas. The new catchment areas follow the natural topography of the project site. This will keep the design cost-effective by allowing the sewer pipes to follow natural slopes and direct water with gravity into the collection system instead of needing to grade the land or pump water over the project area. The catchment areas were designed so that each area contains one manhole or inlet, and these are placed with the natural slope of the land at points of lowest elevation so the catchments can effectively collect runoff and water. After the catchment areas and inlets and manholes were placed, the pipe network was designed. The pipes connect the catchments and manholes and direct water into the retention basin placed on the site. I decided to create an entirely new pipe network instead of using the existing pipe network because it is important that the new design be compliant with the new stormwater regulations and the existing infrastructure is compliant with the old regulations. Here is a conceptual design of the stormwater sewer network system. As you can see, highlighted in pink are the catchment areas, and they follow the lighter shaded gray natural topography of the land. Each catchment area is labeled accordingly, A1 through A39. And then inlets and manholes are placed one per catchment area with pipes directing flow into the 2 retention basins located at A12 and A19. There are arrows in the pipe network that show the direction of the flow, and then highlighted in orange you can see the Shaw Lane power plant expansion. After the sewer system was conceptually designed, hydrological analyses were performed for the whole system. So this included obtaining pipe slopes, which were found by taking the difference in elevation in each catchment area and dividing it by the length of the pipe. Next, a time of concentration or an inlet time of 15 minutes was used for each pipe network, and this was suggested by the Ingham County Drain Commissioner rules. So since this is a requirement, a time concentration of 15 minutes can be assumed throughout the entire project site. And then the rainfall intensity was obtained from the MDOT rainfall table for an inlet time of 15 minutes, a 100-year storm event, and location in Zone 9, which is Ingham County. The weighted runoff coefficients were obtained for the system by evaluating the landscapes of each catchment area and using a corresponding coefficient value from a table. The value 0.5 corresponds to land that is lawn with heavy soil and a slope less than 2 degrees, and the value 0.8 corresponds to land that is asphalt paving, so roads, parking lots, sidewalks, and a value of 0.8 was also used for roofs pertaining to buildings on campus. And you'll be able to see these calculations in a tabulated form on the next slide. The flow rate in each pipe was also found by multiplying the rainfall intensity by the sum of the weighted runoff coefficient times the area of the catchment. The pipe diameter was found by using Manning's equation. The pipe cross-sectional area was found just by pi times that found diameter squared divided by 4, and then a final pipe velocity was found by dividing the flow rate by the area of the catchment. Here you can see a tabulated form of all of the hydrological analyses that were performed. So we have the catchment areas with their area, the slope of the pipes inside the areas, the flow rate of each pipe, pipe diameter, pipe area, and pipe velocity. And ideal pipe velocities will be between 3 to 10 feet per second, and these calculations are shown in the velocity column. And as you can see, the velocities line up pretty well in those criteria. And then, according to commercial regulations, the minimum diameter of the sewer pipes must be 12 inches. So the calculated diameter in my table is below 12 inches, and it would just be recommended in the design to use a pipe that is of minimum 12 inches. The next step in the project design was to design and size the retention basins. I decided to implement 2 retention basins in the system instead of detention basins because the retention basins will eliminate the need for an outflow system, which ensures that the design will meet pre-development outflow requirements, which state that the runoff post-development needs to be less than or equal to the pre-development outflow. And then the retention basins also need to be able to manage 2 100-year storm events. So the first step in sizing the retention basins was to calculate the volume needed to manage the 2 100-year storm events. This was calculated by multiplying the total area of the project site by a value D, rain depth, and this value was obtained from the NOAA Atlas 14-point precipitation frequency estimate table for our project site. This value was 5.46 inches. And then multiplied by the runoff coefficient for our site, which was 0.7. And this yielded a total volume of 3.12 acre feet needed to be managed by the retention basin system. So based on this volume, I determined dimensions for the 2 retention ponds, and the surface area of each pond will be 0.3 acres with a depth of 5.2 feet. Each retention basin will include natural features such as vegetation that will filter water, and they will also include sloped walls. The final step in the design process was to implement low-impact design features. These features are meant to decrease runoff and impervious surfaces and to make the design as cost-effective as possible. The lid features chosen to be implemented in the design are sediment forebays that will act as natural wetlands, filtering vegetation and plants, and a rain garden. All of the lid alternatives and options, these were determined to be the most effective and cost-efficient features for the site. The sediment forebays are the main component that will act to reduce runoff and improve the water quality of the retention basins. The forebays will be placed before the retention pond to collect sediment and filter water before it enters the retention pond. The collected sediment in the forebays can be scooped out for maintenance. Both the forebays and retention ponds will mimic natural wetlands, and this will include wetland vegetation. The vegetation will filter water to improve water quality and will also reduce runoff by evapotranspiration. Similarly, a rain garden will be placed between the forebays and the retention ponds, as well as around the site. The rain gardens will contain plants that collect runoff that will be utilized by the plants or released into the evapotranspiration process. At the end of the design process, a stormwater system cost analysis was performed. Using MDOT's 2019 average price item report, the items incorporated in the cost analysis include sanitary manhole, 12-inch sewer pipe, sewer backfill, lid features, engineering design fee, and earth excavation for sewer piping and retention basins. This table shows the calculations and costs for each item. The average awarded price cost for the sanitary manhole and 12-inch sewer pipe were multiplied by the amount of catchment areas, which was 39. With the excavation cost estimate, it was determined that the type of excavation was earth excavation, and to obtain the total cost for pipe excavation, the total length of piping in the network was multiplied by 2 feet, which is the average depth of excavation needed for sewer piping. The total length of piping in the system was 3,039.8 feet, and this number was multiplied by the average awarded price for excavation from the MDOT table. Similarly, the total cost for the excavation of the retention basins was calculated by multiplying the total volume of the basins by the excavation average awarded price. The sewer backfill price was calculated by taking the total length of piping, and those are the pipes with a 1-foot diameter, and multiplying them by the average awarded price for sewer backfill. This price was then divided by 2 because the pipe takes up about 1 foot of the 2 feet being backfilled. The lid features in the design were estimated to cost about $500,000 based on MDOT past projects, and the engineering design fee was estimated to be 8% of the total cost. The total estimated cost for the storm water network was calculated to be about $3 million, and all of these calculations and costs can be shown in this table.
The Shaw Lane Power Plant, seen in the first image, was in service from 1947 to 1975. In 1993, during routine inspections, MSU personnel noticed oil-stained soil around the southeast corner of a concrete pad, which used to act as an anchor to a transformer. This observation caused further investigation involving 79 hand-augered soil borings around the concrete pad. In 1994, Swanson Environmental was hired by Michigan State University to conduct a secondary collection of an additional 39 soil borings around the entire southern boundary of the plant. The collected borings showed substantial polychlorinated biphenyl contamination, so 104 more borings were conducted in a gridded pattern around the power plant. The results showed 2 major areas of PCB contamination at the site. The first area is located in the immediate vicinity of the transformer, and the second is located in the area south of the power plant, which can be seen in the figure. In the first area, the cause for this contamination is unknown and cannot be definitively linked to the transformer. However, in the area south of the power plant, the contamination is most likely due to the previous storage of dielectric fluid. It is also very important to note that in both cases, the area of contamination decreases with increasing distance from the area. To ensure the contamination had not spread further than the soil, groundwater was also sampled around the plant. All monitor wells were sampled. The groundwater samples immediately down gradient of the spots with the highest concentrations of PCB did not have any detectable PCB concentrations, and therefore the groundwater was not an area of concern. According to the U.S. EPA, under the Toxic Substances Control Act, or TSCA, any soil with PCB concentration greater than 50 ppm needs to be incinerated or disposed of at a chemical waste landfill. Any remaining area that falls between 1 and 50 ppm is under Act 307 Type B cleanup and must be reduced to a lower risk level. Based on the extent of the contamination, excavation of the soil is necessary. Approximately 295 to 375 cubic yards of soil exceed 50 ppm and need to be excavated and properly disposed of. The best option for this is performance-based disposal because contamination is not detected in the groundwater and the EPA does not need to be notified and approved for this type of disposal. It is recommended, however, that the regional PCB coordinator be contacted in the event that this solution is employed. This method involves the disposal of contaminated non-liquid materials to a TSCA chemical waste landfill. The closest EPA-approved commercial waste facility is Clint Lights Recycling, located in Mason, Michigan. The remaining 1,200 to 2,040 cubic yards that fall between 1 and 50 ppm are under Act 307 Type B cleanup, as stated above, meaning that these areas need to be treated and reduced to an acceptable risk level. It is recommended that this area be reduced to 10 to the -6 risk-based level because of its carcinogenic properties. The approximate price was totaled to be $132,550. For more information of action taken to the remediation site as of May 2005, the approved memorandum stating the contract details can be provided upon request.
Pavement engineer responsibilities include analyzing existing pavement conditions for both Shaw Lane and Reed City Road. Those are the two roads in question. Gathering data on climate, soil borings, traffic demand, and the existing pavement. Considering different design alternatives for each road, which include mill and fill, asphalt overlay, new flexible design, and new rigid design. Also choosing an alternative based on the pre-existing conditions and the gathered data, which is climate, soil boring, traffic demand. And then comparing costs for each design alternative using cost per lane mile, and then comparing those costs with LCCA, which is life cycle cost analysis, and then finally calculating total capital costs for the chosen alternative and coming up with a design cross-section. Every road construction project has standards set at either the county level, the state level, or the federal level. For both the roads in question, the Ingham County road standards will suffice. Both Shaw Lane and Red Cedar are in urban areas with medium residential capacity due to proximity to dorms. For full depth bituminous pavement, the width of the right-of-way shall be 60 to 66 feet. Curb and gutter face-to-face shall be no less than 30 feet. Top asphalt layer to be 1.5 inches. Base asphalt layer to be 6.5 inches. And aggregate base to be 6 inches. For concrete pavement, width of right-of-way is 60 to 66 feet. Curb and gutter face-to-face is 30 feet. Portland cement concrete is to be 7 inches. Longitudinal lane tie spacing to be 21 inches. And transverse lane tie spacing to be 12 inches. Lane width for both asphalt and concrete will be 12 feet. These are all minimum values. All standards are within MDOT standards. And as you can see on the slide, it shows it in the table. And on the right is the default truck factor values. This will be used when calculating easels. Using LTTP bind, the PG of the binder and the climatic data was found for both Shaw Lane and Red Cedar Road. Both these roads are close together, so the PG grade of the binder will be the same because the weather is not different from one road to the other. The lowest yearly air temperature for this area is negative 28.9 degrees Celsius. Highest 7-day air temperature was 51.8 degrees Celsius. The lowest pavement temperature of the 98th percentile was negative 27.5 degrees Celsius. The highest average 7-day pavement temperature in the 98th percentile was 58.15 degrees Celsius. And from this data, the PG selected was PG 5828. Can also be seen in the two tables on the slide. existing pavement condition data was gathered by fellow pavement engineers. Some of us were not allowed on campus due to COVID. As you can see on the left is Red Cedar existing pavement, and on the right is Shaw Lane existing pavement. Shaw Lane is considerably worse than Red Cedar, and the parking lot was deemed unnecessary to redesign because it was also in good condition. Shaw Lane had a lot more alligator cracking and noticeably worse transverse cracking than Red Cedar. Red Cedar had about 10 to 20% alligator cracking, which is not all that bad. Soil boring log data. We were provided a log of soil borings for the area around Red Cedar and Shaw Lane, which from there I chose a soil profile, which concluded modular slope rupture of the soil for Red Cedar and Shaw Lane was to be 3,800 psi, which can be seen in the table for both Shaw Lane and Red Cedar. For traffic demand, ADT, the average daily traffic, which was given by the transportation engineer to me in this top left table. You see the averages for West Shaw Lane, Red Cedar Road, the intersection, South Shaw Lane, and North Shaw Lane. The averages were taken from the table on the right. You can see ADT for Shaw Lane was 10,873. For Red Cedar was 5,355. And from there, easels for a 20-year lifespan were calculated using the ADT, the percent trucks, the growth factor, truck factor, lane distribution, and directional distribution. And the easels for Shaw Lane for flexible pavement came out to be 1.4 million and 2 million for rigid pavement. For Red Cedar, the flexible pavement easels was 500,000 and the rigid pavement easels was 700,000. 4 design alternatives were considered for both roads, Shaw Lane and Red Cedar: overlay, mill and fill, new flexible, and new rigid. Each existing thickness can be seen in the table on the slide. Also, every new thickness can also be seen for each alternative. Pave Express online was used to get the new thicknesses. Any thickness that is above the existing HMA thickness, which as you can see in the table is 5 inches, so say the new overlay HMA 7.5 inches and 6 inches, would be considered not feasible because we would like not to raise the road profile. We want to keep the road profile the same, meaning that the existing HMA layer, which is 5 inches, should be equal to the new existing HMA layer, keeping it 5 inches. After getting a new thickness for each alternative from Pave Express, a cost per lane mile was calculated for each alternative for both roads using the material cost given to us in D2L multiplied by the volume of material used per lane mile. All the cost per lane miles for each alternative can be seen in the table at the bottom for overlay, mill and fill, new rigid, and new flexible. As we can see, as assumed, overlay will be the cheapest option using cost per lane mile only. But after getting cost per lane mile, we needed to compare each of the alternatives using LCCA, which is life cycle cost analysis. And as you can see from the two tables, Shaw Lane equivalent annual unit cost and Red Cedar equivalent annual unit cost, equivalent annual unit cost being the second column and present worth being the first column. Present worth meaning this is what present day costs would be for each alternative, and equivalent annual unit cost being cost per year today, what each alternative would cost. We could see that asphalt overlay is still the cheapest, but as we talked about earlier, asphalt overlay would raise the road profile of the road, meaning that it is not feasible for our purposes. So for Red Cedar, a mill and fill will be sufficient for us, considering that the existing pavement conditions of Red Cedar are not all that bad. And for Shaw Lane, a new flexible road is the most feasible, considering asphalt overlay would raise the road profile and mill and fill would not cover all the damage seen in the existing pavement conditions. Finally, the final cross-section and project cost estimate. Total cost of mill and fill for Red Cedar will be $100,000, including milling, excavation, and the asphalt fill. Total cost of new flexible construction for Shaw Lane will be $250,000. In total, the cost of payments for Shaw Lane power plant will be around 350,000. And the Shaw Lane final cross-section for the new flexible pavement can be seen on the left. And then the Red Cedar final cross-section for mill and fill can be seen on the right. The limits for Shaw Lane are Chestnut Road to Red Cedar Road, which is 0.3 miles. And the limits for Red Cedar are Chestnut Road to Shaw Lane, which is 0.5 miles.
To accomplish the transportation design for this project, first we need to view the project plan and expand goals that need to be done. Second, analyze the existing traffic condition, including traffic capacity, turning movement, and so on. Then, design new road plan and develop the traffic system and interrogate the safety for the objective area. The last is to determine the cost for the new traffic system. According to the design goals, the North Shaw Lane will be blocked for the future plan, and the South Shaw Lane will be expanded to a two-way four-lane road. Since the objective areas is located at the university place, so the road will be designed for the 20-year period, and with a 1.5% growth rate for the vehicle volume. To get an overview about the current traffic condition, data analysis is the most important and effective way to do that. Thanks to the data that offered by the MSU and Tri-County, we can still do the traffic analysis for this project at this unusual year. The table on the left side is the traffic volume for each movement at the intersection of South Shaw Lane and Red Cedar Road, and it's used as a sample to calculate the peak hour, which has the highest traffic volume during 1 hour for a day. Then this volume number will be used to calculate the PHF, also known as peak hour factor, which represents the maximum traffic capacity of this intersection. Since PHF usually ranged at 0.25 to 1, 0.87 is a relatively high number. Then we can know that the traffic data during mid-time will be used to determine the signal timing and further research, which will be discussed in the later slide. By using the turning movement data that offered by the Michigan State University, we can make the synchro modules for the current transportation intersection. Then, by calculating the traffic volume after 20 years design, another synchro module can be made for the future 20 years. Then, by comparing these two graphics, we can know that the increase of the traffic volume at each direction at this intersection will not affect the total delay dramatically. And we can see that by looking at the level of service in the graph. After the step of analyzing transportation data, we finally get to the process of redesign of road plan. From this graph we can see the North Shaw Lane has been blocked, and the South Shaw Lane has been expanded to a two-way four-lane road, and it will be allowed to travel from the east to the west, which is the function that the North Shaw Lane originally has. Then, we need to design about the stopping side distance. From the table, we can see there's the stopping side distance for each speed. Since the campus area should be set at 25 miles per hour speed limit, the stopping side distance will also be set as 155. Otherwise, considering about some emergency situations, the speed limit will be set at 30 miles per hour, which also means the stopping side distance will be designed at 200 feet. The next important factor is to design the turning radius of the intersection. From the graphic, we can see the turning radius we have for the turning at each direction. And according to the reference table on the right, we can see that most type of vehicles, especially the buses will be allowed to make the turns at this intersection. However, the single unit truck with 3 axle will not be able to make the right turn from the north side of the road. On the other hand, this type of vehicle is a rare type of vehicle that can be seen on the campus, so this design should be acceptable. After redesign the road plan, we need to go back to the synchro and build a new module to test if the new intersection is able to run with the same traffic capacity that the current intersection has. From this time window, we can see that the new intersection is able to run the traffic volume at a reasonable level of service. Even though the level of service at left turn from the northbound is at a sea level, it is still an acceptable result concerning about the increasing volume of the traffic. For the cost of transportation design, the most major part is the removal of North Shaw Lane and 6 pedestrian signal light system. Then 4 more traffic signal light system will be added into the new plan. And the final cost we can see on the table, which is around $630,000.
Here you can see the overall cost for our project. The cost of the structure has the most significance, followed by the hydrology aspects. I will give you a moment to look over the details in these tables. Here you can see that we have 5 phases for our construction project. Phase A focuses on demolishing Shaw Lane Power Plant and clearing of old materials that is inside of it. Phase B focuses on implementing new pavement and road changes on Red Cedar Road and Shaw Lane. Phase C focuses on the addition of the south building that is connected to Shaw Lane Power Plant and new structural updates to the Shaw Lane Power Plant. Phase D focuses on removing and the proper disposal of the contaminated soil and the remediation of green spaces. Phase E focuses on finalizing the interior structures and cleaning up construction so that the building is ready for occupancy. To give a brief summary on our project, it will take 12 months, it will cost over $15 million, there will be an additional south building connected to the Shaw Lane Power Plant, and Shaw Lane Red Cedar Road remediation will take place during this time. PCB contamination will be removed from the soil surrounding the building, and a new stormwater management system will be implemented. Thank you for listening, and please send any questions to the email listed below.